Let's consider now pH and polyatomic or polyprotic acids. I'm going to start by teaching the example with H3PO4 phosphoric acid. And that's generically represented by this triprotic. Triprotic meaning it can give off a max of 3 protons. Now, it actually doesn't do it in one step. Normally, you were taught in Gen Chem 1, H3PO4 gives you 3 H's and 1 PO4 and 1 phosphate. Well, that's what happens, but what you didn't know is it actually happens in 3 steps. 1 proton comes off to give you a new species, and then a proton comes off of that one to give you a second anionic species, and then finally the last proton comes off to give you, in this case, the phosphate anion. Now, what you need to know is that each of those steps is a reaction and they are not equal. They have very different Kas. And what you will see generally true is the Ka of 1 is always greater than the Ka of 2 is greater than the Ka 3. So why is that? Well, because as you continue on, this is a device to think about this. This anion becomes more and more negative, and that makes it harder for the positive charge to depart. Hence the lower Ka as you go down the line. So now looking at phosphoric acid, you can now see that trend. And as an example, I have each of those Kas shown. And you can see that the Ka1 is much, much larger than the Ka2, which is much, much larger than Ka3. That is a general trend and general knowledge. So the question is, well, how do I calculate the pH of a phosphoric acid solution? Because I've got protons coming off at a bunch of different places. And the short answer is the pH, or the H plus concentration, is going to be the sum of these 3. So what that means is, to calculate it, you're going to have to do the calculations for 3 different reactions and then add up the H plus values in each of those. So let's move to this problem as an example. Calculate the concentration of all species in 0.1 molar phosphoric acid solution. And as I just told you, you have to do 3 calculations for each step. And what that means is, by calculations, I mean 3 different Rice equations. There's one for each step. So let me walk you through that ebb and flow, and then we'll go back and look at this particular example. Right. For phosphoric acid itself, we know it's going to give up a proton and it's going to generate this single negative charged anion. And you're going to use the regular Rice equation. And since the 0.1 was given, and since the Ka of this was given, or you could look it up, then you can calculate the H plus concentration, same as you did before. But what you need to know in this case is, you now know the H plus concentration. X is now equal to the anion concentration. And it's this concentration that you're now going to use, as the green arrow shows here. So now you have a new concentration of your starting material. It's no longer 0.1. It's now whatever this X value was. This X value is where you start. Okay, now it's time for Rice equation number 2. Well, you know this species is going to give up an H plus and going to generate a second anion. How much does it lose? I don't know. So we're going to call the amount that it loses Y to differentiate it from X. So this is now X minus Y. How much H plus is going to show up? Y. So how much HA2 minus is going to show up? Y. So here we have it. So now what is my total H plus here? Well, it's X, right? Now notice, I started out here at X because I ended here with X. And I started here with X. Why? Because I ended here with X. So you can see my new values after the second step are My concentration of H2A minus is X minus Y, and my concentration of X plus is X plus Y. And this just continues to the third step until you complete the problem. So now let's look at that real time. I've done the calculation here for Ka1 and Ka2 and Ka3, by the way, are given. And so let's do that. So as I look at these, I don't know these three values. I do know Ka1 and I do know the initial concentration. Okay? Rice equation, the Rice equation, you can work that out. Really, I would probably just use the shortcut. But in this case, I did work it out using the quadratic. And remember, where all of this looks busy, this is just Ka from this equation. So, right. So when I do that, I get that the H3PO4 concentration is this, and I'm able to calculate X. Right. So now I have to start the next question, right? So now I need to know what Y is. I need to now know what the final HPO42 minus is going to be. See, and all of these values I had from working through the Rice equation, I'm just going to plug in here. And these values that I'm plugging in, what I'm doing is I'm illustrating here where I got those from, so you're not overly confused. Okay, in this case, we actually could disregard these, and so we could go straight to using our shortcut for a weak acid. I now know this value. Finally, I do it a third time. Instead of calling the change X, or calling the change Y, this time we're going to call the change Z and work through it one more time. I now have three equations where I have determined H plus concentrations. Yes? So now it's just a matter of what is your H plus concentration for this solution? It's the sum of all of your H pluses from each step, which is this number plus this number plus this number. The final thing I want to mention is if you are starting here with a strong acid, this greatly simplifies things. For example, let's say we're using sulfuric acid instead. We know this is one of your 7 strong acids. And we know the first step is to lose 1 proton. But guess what? This is a strong acid, so you automatically know whatever this concentration is, you already know that. So, in other words, because it's a strong acid, you don't have to do a Rice equation for that step. Why? Because you know that the concentration, that the hydrogen ion concentration for a strong acid is just equal to Ca. And now all you really have to do is to just do one calculation for the second step, which does have an equilibrium Ka constant.